All right, so continuing where we left off, we were about to go with example 4, so that's where we will begin. All right, so A is we're supposed to graph each polar equation. Confirm by converting to a rectangular one. All right, so R equals 2. Just as a side note, you know that the equation of x equals a number, like 5, is a special graph. It's a line that's vertical. Notice that equation doesn't have a y in it. And y equals a number, like -3, is also special. It's an equation that doesn't have an x in it, and it's a horizontal line. So there are special polar ones like that, akin to that, where you have r equals something. There's no theta in this problem. And so this one's actually pretty easy because what that means is that for every point on this graph, r is always 2. Doesn't matter what theta is, r will be 2. So we let theta take on every real value, keeping r at 2, and we get like at 0 here, pi over 6, pi over 3, pi over 2, etc., etc. And what we're getting, of course, is a set of points where the radius is always 2. That's a circle centered at the origin of radius 2. So to confirm that that's what we're supposed to be getting, this is the case where we're converting, and you can either multiply both sides by r or square both sides. Squaring both sides is actually really helpful here. So r squared is equal to 2 squared, which is 4. And going to rectangular coordinates, r squared is equal to x squared plus y squared. And of course, that's the equation of a circle centered at the origin with a radius of 2, which is exactly what our graph looks like. So r equals a number is really, really easy to graph. Okay, theta equals a number. If you think about it, that means that theta is specified. R needs to take on all real values. So let me draw a few circles here. And I could have a radius of 0, which would be that pole point. I could have a radius of 1, or 2, or 2.5, or 3, or 3.5, 4, whatever. And so I'm getting a whole bunch of points that seem to be lining up with each other along the angle pi over 3. But please don't forget, r in this world can also be negative. So with pi over 3, -1 for r would be here. -2 for r would be here. And again, looks like we're lining up. So the equation theta equals a number is a line that passes through the pole at the angle given. Okay? So let's convert this to rectangular coordinates to kind of confirm. So to do that conversion, I know that the tangent of theta in terms of y and x is y divided by x. Let's see, the tangent of pi over 3 is 1 over the square root of 3. Make sure I've got that right before I go on. Tangent of pi over 3. This is what happens when I can't think of something. I draw a picture. So here's pi over 3. That means this is 1, 2, square root of 3. Nope, I had it wrong. The tangent of pi over 3 is square root of 3 over 1, which is square root of 3, equals y over x. And if I multiply both sides of that equation by x, I obtain the equation of the line y equals square root of 3x. That's in y equals mx plus b form, where the b, the y-intercept, is the pole, and the slope is square root of 3. Cool. And so that looks right. And that's that rectangular equation. Very good. Now, let's see. C. Go move this down a bit. Okay, in C, we have r equals secant theta. So again, my trick is either multiply both sides by r or square both sides. Since that's not sine or cosine, multiplying by r won't help, and squaring I don't think will help either. So let's do a different tack. Let's try rewriting this in terms of sine and or cosine. Since the secant of theta is 1 over cosine theta, yes, you still need to know all of your identities from pre-calculus. We can write r is equal to 1 divided by cosine of theta. So if I multiply both sides of that equation by cosine theta, lo and behold, I actually end up with r cosine theta, which is good, because r cosine theta is x. Okay, now, how would we have graphed this from polar? Well, if you think about it, if you were to make a table of values, that's going to be really hard, because what we're supposed to get from that is a vertical line, x equals 1. Can you imagine the weird values you'd get to get all of these points and all of these points? And so it might take you a long time to make a table of values and figure out that this is a vertical line. So in this case, it seems like it's actually easier to graph once it's in rectangular form, as opposed to trying to graph from polar form. You should be able to do for any problem whatever is the easiest and most efficient. And like the r equals a sine theta that we mentioned earlier, that one you can graph now very easily because of the techniques we talked about before. So you're going to have to just get good at it, at seeing what's the appropriate way to go. Alrighty. So if you look at the next slide, it says the graph of r equals 1/2 theta is shown. And you can see that you can do that in parametric mode. Remember, x is equal to r, 1/2 theta, times cosine theta, and y is equal to r, which is 1/2 theta times sine of theta. And in a graphing calculator, they decided to go from -4 pi to 4 pi, which creates a spiral. So anytime you have r equals a number times theta, you will get a spiral. And that's, of course, only part of the spiral. They didn't keep going. Technically, to get the whole spiral, you'd have to graph from -infinity to positive infinity, which on a graphing calculator is actually impossible. But that's all right. We will take that as given and go on. All right, next. To find the slope of a tangent line to a polar graph, consider a differential function given by r equals f of theta. To find the slope, we're going to want to find dy dx. And so what we're going to do is we're going to go to parametrics. And since x is r cosine theta, that's going to be r, which is represented by f of theta, times cosine theta, and y, which is r, in this case f of theta, sine of theta. And then, thinking of it parametrically, if we want to find dy dx, we're going to have to first find dx d theta, which we can do with the first equation we wrote. Since this is a product, you'll have to use the product rule. First times the derivative of the second plus second times the derivative of the first And then we'll have to find dy d theta. Again, it's going to be a product, so we use the product rule. First times the derivative of the second plus second times the derivative of the first. Then, just like what we did with parametrics, if we want to find the first derivative of y with respect to x, in other words dy dx, we're going to have to form the ratio of dy d theta divided by dx d theta. This is just like what we did before, it's just your parameter this time is theta instead of t. And so dy d theta is this expression that we just wrote. And when I've written this down, you'll see it as a completed thing, and you could memorize it as a formula. I wouldn't. I would actually set up the parametric equation for that specific problem and find dy d theta and dx d theta separately, and then form the quotient of those two things, as I'm doing here, but with specific results. So, and it will involve the product rule because it's always r times cosine theta or r times sine of theta. Okay. And like I said, I would not memorize this formula. I don't think it's worth memorizing. Just do it on a case-by-case basis. But that's what dy dx is going to be every time. All right. Now, moving to the next item. If we have dy d theta equaling 0, if dy d theta equals 0, then that implies that dy dx is 0 over something. I'm just going to call that something a for simplicity, which simplifies to be 0. And this slope being 0 means you have a horizontal line, so a horizontal tangent line. When to the curve when dy d theta equals 0. If you have dx d theta equaling 0, that will be something over 0, which is undefined. And if the slope is undefined, that means that it's a vertical line. So that would lead us to the conclusion that we have a vertical tangent line. Okay. Now, there is a possibility that you would have both 0 at the same time. Oops, hold on. Wrote the wrong thing. If dy d theta and dx d theta are both equal to 0, when we talked about limits, that was 0 over 0 was indeterminate. And that means that you're not going to be able to draw a conclusion from the fact that they're both 0. You just won't know. So dy dx in that case would be 0 over 0, which is inconclusive. because we don't know what that number could be. Remember when it was limits, 0 over 0 could be anything. It could be equal to 5 or 0 or 13 or infinity or whatever. There were a lot of different possibilities. So we won't be able to draw a conclusion if they're both equal to 0 at the same time. Okay. All right. So the next example asks us to find the horizontal and vertical tangent lines of r equals sine of theta. Where theta is between 0 and pi. Alrighty. So we're going to start by saying we know that x is r sine of theta times cosine of theta, r cosine of theta, and y is equal to r, which is sine of theta, r sine theta. So r sine theta times sine theta. In other words, sine squared theta. So what we're going to do here is to find these tangent lines that are vertical or horizontal. We're going to need to find both dx d theta and dy d theta. Okay, so this is a product. So the derivative will be first function times the derivative of the second function plus the second function times the derivative of the first function. Okay, which turns out to be negative sine squared theta plus cosine squared theta. Which simplifies to be cosine of 2 theta. Again, you're going to need to review your trig identities because they will be important. And like this double angle identity is something you're expected to know. All right, dy d theta, since that's a general power rule problem, is going to be 2 times the sine of theta to the first times the derivative of the inside function. The derivative of sine of theta is cosine theta. And that simplifies to be sine of 2 theta. Okay, so what we're going to want to do is find where dx d theta equals 0. So that means cosine of 2 theta is equal to 0. So 2 theta is going to equal pi over 2 plus multiples of pi dividing by 2, you get theta equals pi over 4 plus multiples of pi over 2. And in the range that was given, we were looking for values on the range 0 to pi. Pi over 4 is a good answer. If I add pi over 2 to that, that'll be 3 pi over 4, which is also a good answer. So what that says is we have vertical tangent lines when theta is pi over 4 and when theta is 3 pi over 4. Okay. Now for the horizontal tangent lines, we want dy d theta to equal 0. So sine of 2 theta equals 0. So 2 theta is multiples of pi. So theta is multiples of pi over 2. So within our range of values, let's see, we do include 0, so 0 times pi over 2 is 0, so that's good. And then 1 pi over 2, still good. And that's the last one. So when theta is 0 and when theta is pi over 2, we'll have horizontal tangent lines. Okay. And if you think about it, this is one of those that's r equals a sine theta, where the a is 1. And so as we said before, let's make this 1. The center will be on the y-axis because it's r equals a sine theta. The diameter is the a value 1, and a point on that is the pole. And then I could go pi over 6 will be 1/2, and 5 pi over 6 will be 1/2. That gives us a couple of nice points to plot. We get this circle, and if you look at that circle, doesn't it indeed have at pi over 4, doesn't it have vertical tangent line, and at 3 pi over 4 doesn't have a vertical tangent line? That makes sense, right? And then at 0, you have a horizontal tangent line, and at pi over 2, you have a horizontal tangent line. And that certainly makes sense. All right, that's the end of this little section. We'll come back in another section to finish this up.